So in this little section, we're going to look at how the band diagram is formed, and then at the end derive an equation that tells us about the relationship of all the given parameters, meaning things like the metal work function and the semiconductor work function and electron affinity, and how those eventually translate into the surface potential, which of course is the one that really controls the charge density in the channel. So let's look at our given quantities for the three materials and draw a band diagram before we assemble the MOS structure, and then look again at the band diagram after we put them all together. So the metal, we only have to define the work function, which is the distance to the Fermi level. And this is the vacuum level here. Okay. The oxide, in the absence of any built-in voltage, looks something like this. You have a band gap of something between 8 and 12 electron volts, and then it has a very small, usually assumed to be very small, oxide, electron affinity. And then the semiconductor, before it's connected, has of course straight band edges, straight EI, and the Fermi level, we're going to look at a p-type material here, so EF is here. So this is our phi FP. This is our semiconductor electron affinity, and this is our semiconductor work function. And I'm going to write out semi there for the work function, just because we're going to introduce the phi surface in a minute, and it has the same natural notation. So the built-in voltage here is, like all junctions, going to be determined by the difference in Fermi levels, or the difference in work functions, really. So what we have to do, if we clamp the metal, we have to imagine sticking the band edges of the semiconductor onto the oxide and then pulling up until the Fermi level becomes equalized. And what that's going to do is it's going to drop some voltage across the oxide, and it's also going to induce some band bending in the semiconductor. So let's redraw this diagram after the connection together and see how it changes. So after we connect them together, we're going to actually start by drawing in the vacuum potential. And because of these electric fields and space charge regions, there's going to be a real potential induced. And so the vacuum level actually needs to look like this. So our metal side doesn't change. Our oxide now has a linear slope in its bands, which means that there's a constant E field inside the oxide. And our semiconductor, as you can see here, is going to develop a space charge region. So on this diagram, we're going to reference our electron affinities and metal work function to the conduction band edge of the insulator, or the oxide. So that means we're going to take the original values and we're going to subtract off this amount of chi oxide. So we can write this distance here is E chi semiconductor prime, and this distance right here is E phi metal prime. So we've just taken the original values and subtracted off this much. And that just keeps the notation a little more compact. We don't have to write out some extra terms when we start summing and subtracting voltages. So our surface potential appears right here. So now we want to come up with an equation for the surface potential in terms of all these given values. So we're going to start over here at the metal, and we're going to write out an equation that has to sum to 0 because we're going to go around a closed loop and come back. So we start at the Fermi level, and we're going to say 0 equals E phi metal prime plus the amount of voltage that's dropped across the oxide. And this is a little tricky value to, this is a little tricky voltage to get at, so we're going to come at it later, try to calculate it through the capacitance. So then we've made it up to this point. Now we're going to go down by chi s prime. And now it turns out to be better to go all the way out away from the junction for a moment and then come back. So one thing we want to notice here is that if we excuse me, I've just noticed that this needs to be extended slightly. So the surface potential is the amount of band bending in the semiconductor. And here we've measured off the intrinsic level, but it's exactly the same as if we measured off the conduction level. So this value here is also E phi s. So if we subtract the electron affinity and then we add E phi s, we're back at the conduction band here. So plus E phi s. And then we want to go down across the band gap. So minus E gap, and then up to the intrinsic level, down from the intrinsic level to the Fermi level, and that will mean we've actually completed the loop. So we go down by EG, up by EI, and then down by EFP. And that lets us complete the loop and know that this whole thing has to sum to 0. So now we can rearrange this and solve for the surface potential plus the voltage drop across the oxide in terms of all these other values. Now an important note here is that this value here, for in general, I've written it out for any semiconductor, but for silicon, because EI is always really close to half of the band gap, what this quantity really comes out to is minus EI, because E gap over 2 is very close to EI for silicon. Now for gallium arsenide and other semiconductors, that's not true, but because 99% of the MOS structures in the world are made out of silicon, we're going to make this assumption. Okay, so after some rearrangement of this equation, we can get the oxide voltage with 0 applied voltage plus the surface potential at 0 applied voltage, and it all comes out to the reduced metal work function minus the reduced semiconductor work function plus E gap over 2E plus phi FP. And again, let me point out this is only for silicon that you can write it this way. Now we can take this, this whole quantity here in brackets and define it as negative phi metal semiconductor. So this is like the metal semiconductor work function difference. And if we look back here on this diagram, what we're really saying is the total voltage change here has to add up to the amount of change in the vacuum level, and we know that has to, in the end, add up to the change in work functions between the metal and semiconductor. So then we can identify this quantity here as the work function of the semiconductor. There's two important special cases. It becomes actually very convenient to use, instead of the metal, to use heavily doped polysilicon for the gate metals. So in the case of, let's say, an N+ semiconductor, here's our conduction band, here's our valence band. And for N+, it means that the Fermi level is exactly at the valence band edge for, I said, this is the P+ case, and then in the N+ case. So in those two limiting cases, the work function for the p-type case is equal to the electron affinity plus E gap, and then for the N+ case, it's just the electron affinity. So in these two cases where we have a p-type substrate and we can put either a P+ or N+ polysilicon gate material, the metal semiconductor work function difference reduces to pretty simple forms. We're going to have two cases if we use P+ or N+. So for the P+ case, we have that this is equal to E gap over 2 minus phi FP. This is for the P+ case. And then in the N+ case, we have negative E gap over 2E. Again, this is the two different heavily doped gate metals that you can deposit onto a p-type material. And of course, the equation changes a little bit if you have an N-type substrate and you put either the P+ or N+ gate metal, polysilicon gate metal down.